long to go in on or grading?
All right, how are y'all doing? Y'all ready for spring break? Still got a ways to go.
Summer.
Ready for the summer break. We've got what, this week, and then we've got 2 more weeks, and then we've got a little break, huh? All right, so I'm trying to update grades, and I have changed the grades. If you go in, you'll see quiz grades have changed, and I think there was one quiz that I had handed back, and I didn't record it for some people. So look, what I want you to do is get all of your quizzes together, everything that you have, and if it looks like online I'm missing something, then what I want you to do is turn in what it looks like you're missing, okay? And then I will make sure I put those grades in. Sound fair? Okay. I will let you come collect these later. And let's get started. Any questions over anything, homework or anything else? No? So how was the homework? Any issues? I mean, did you run into any problems or find anything difficult?
No, it's just easy to forget.
Okay. All right, well, last time, what did we do?
We were doing cosine, secant.
We did secant, cosecant, cotangent, and tangent, right? Those were the ones we focused on. And now what we're going to do is move on to 7-8, which is phase shift. And we're going to kind of bring it all together, all right, with one final kind of couple of formulas. Some people like to work off formulas. Some people, I prefer to work like I've been, where I'm just, setting the argument equal to the either 0 and 2 pi or 0 and pi or whatever it is, and just working it out as opposed to having to memorize different formulas for things. It's just preference, but I will provide you the formulas. But before I did that, I wanted to do an application. Just a problem to get you to see, like, what would be the value of actually having these functions in our toolbox of functions, right? Like, where would you ever come across a secant function or a cosecant function, all right? So there is a problem that I do in Calculus 1 that goes something like this, all right? Now, this is going to be worded as it will be worded in Cal 1, so don't get too bogged down on the actual question, because I'm not going to ask you that question on a test, all right? So here's the problem. A plane flies at 400 miles per hour at an altitude of 2.5 miles. A radar station on the ground is tracking the plane. At the moment, the plane is exactly 4 miles away And when I say away, I mean from the radar station, okay? At the moment the plane is exactly 4 miles away, how fast is the radar rotating? Now I have to explain this with a picture, all right? Because we need to make sure we understand what's going on here, all right? But that's the question as it would be posed in a Calculus 1 class. All right, so here's the picture. You've got the ground, and you've got this little radar station on the ground, all right? That's a little radar, I know, again, impressive. So that's a little radar dish or whatever, okay? And it's tracking this plane that's flying overhead. The plane is 2.5 miles high, and it's traveling at 400 miles per hour. And we're just going to assume that it's flying horizontally, and we're also going to neglect the fact that the Earth is curved. All right, we're just going to simplify the problem, straight lines here. So now you have a plane, right? What do you want? B-52, F-16. I can do anything. I'll just go with my standard. There you go. There you go. I know. There's a little thrust coming out the back there. Okay? So there's my plane flying overhead. And so what we're doing here is we're imagining that the plane is moving, right? And as the radar station is tracking it, what I mean is this little dish has to kind of keep its eyes on the plane. So it's rotating. As the plane comes this way, the radar has to rotate, right? And then as it passes over, it'll start to rotate like that. So, understand?
I don't think it does.
What do you mean? You don't think they work that way?
It doesn't work that way.
Well, okay, so what if I make it like an anti-aircraft artillery battery or something like that, okay? All right. I was trying to keep it, you know. All right, so whatever it is, look, let's change it from a radar to a guy with binoculars, whatever. But he has to track it, okay? So this is rotating, yes? All right, so if this is rotating, we can imagine that there's like an angular speed, isn't there? And my first question is that angular speed constant? Is it always rotating? If it's tracking this plane, is it always rotating at the same speed? Yes or no? What do you think? I'll give you another analogy, a different analogy. Well, we don't live where there's subways. Anyone ever been to a subway station? Okay, or you can just think of a racetrack or something like that. You're standing there on the edge of the track and you're watching a car come or a train or whatever it is. And you see it way down there, right? And if it were to just come by you, you know, you're rotating, right? Your head is rotating to keep up with the train. Initially, it would be a very slow rotation as it's coming towards you. But then it would be, you know, really fast, and then it would slow down again, wouldn't it? And that's the same thing that's happening here. When it's really far away, that angle does not have to change much to keep it in sight. But once it gets, you know, closer, this has to speed up the angle, doesn't it? So what we need to do is see if there's any way that we can find a relationship between how fast this is turning and how that's related to how fast the plane is going. Now that's going to be a calculus question. But to do it in calculus, the steps are as follows. Draw a picture, assign variables, and then somehow try and connect the variable that represents the speed of the plane to the variable that you're trying to analyze. So let me draw a picture. Does everybody see that I could, from the plane, drop straight down and create a nice right triangle like this? Yes? That's a pretty natural picture that fits in here. And what I'm looking at here is this angle right here, theta. Right? And I want to know, as this plane moves, of course, the triangle changes, doesn't it? And so what I'd like to do is figure out if I have a relationship between this angle and the speed of that plane, which we haven't talked about. But to do that, what I will do is start assigning any variables or any constants that I know to this picture. So is there anything on that triangle that I know does not change?
Altitude.
The altitude, right? How high the plane is. So I know that this is 2.5. Right? That's 2.5 miles. That's the distance from here to here. Now, what about this side right here? That is the distance from the point on the ground below the plane to the radar station, right? Yes? And does that change as this situation, elapses, as time elapses? Is that side changing? Yes, it will change, right? So since it's changing, I assign it a variable. I'm going to call it x. All right? Now, I also have a hypotenuse, don't I? Yes? And so this distance from here to here, is that changing?
Yeah.
Yes. It does change as the plane flies. And why don't we call that, we could call it h for hypotenuse, we could call it r for almost like a radius, or we call it d for like the distance between, isn't that the distance between the radar station and the plane? I could use anything. I'm going to go with h just for hypotenuse. Is that all right? Okay. So, what sorts of relationships do I have that I could come, just right now, going purely off of what we've talked about in this class, what could I do that would, with trig functions, what sort of trig functions could I set up that would connect these things together? Like, could you give me a trig function that would connect theta and h together?
Sine of theta.
Okay, you could tell me that sine of theta is equal to, sine is opposite over hypotenuse, right? So this is equal to 2.5 over h, right? I'm just saying this is a relationship that I have, right? I have that relationship in this triangle. I also have, what else? Tangent theta. Okay, what is the tangent theta relationship? 2.5 over x, right? I have that. Any others? I mean, you can come up with all of them, right? I mean, all the different trig functions. But those would be nice equations that involve the angle, right? And one of the sides that's changing. So in a calculus class, we look at this and we go, okay, which of these would we want to work with? Well, I want to know at the moment the plane is exactly 4 miles away from 4 miles away, how fast is it rotating? When I say 4 miles, exactly 4 miles away, am I referring to h or x? This is going to be debatable. When the plane is exactly 4 miles away from the radar station, are we talking about x or h? So let's vote. X. Where are all the x's? They went away. Everyone said x. Okay, you can change your mind. Okay, how many of you think it's h? Okay, it's h. All right. In a calculus class, sometimes that can be a little vague, and you could argue, but we're talking about h. So we want to know exactly how fast this angle is changing when that h is 4, right? So I'd be more inclined to use this one than I would this one. Do you understand why? Because the information I have is about h, not about x. We good? I'm not done, but I want to take a look at that equation. I want to write it a different way. So I'm taking this equation. What I'm going to do is I'm going to solve for h. I'm going to get h by itself on one side. So to do that, I multiply the left side by h. I multiply the right side by h. That'll clear the denominator on the right, won't it? And then I get h over here, sine theta, is equal to 2.5. And now what I'd like to do is divide the sine. So if I divide sine, h will be 2.5 over sine theta. When you have sine in the denominator like that, that's equivalent to what trig function? Cosecant. Isn't that the same as cosecant? So couldn't I write h is equal to 2.5 cosecant theta? Couldn't I? So just from the word problem, I drew a picture. From the picture, I came up with a relationship using trig functions. And from that, I could solve for h, and I could get h in terms of theta. I could get h in terms of theta. So h is a function of theta. In other words, I could write it this way. H is some function of theta. Meaning, you give me an angle, right? If you supply me with the angle, whatever that angle is, then this will spit out h. It'll spit out how far away the plane is. Y'all agree? All right. So this is, now at this point we can't do any more because we would do calculus at this point. All right, we're not there. But that part of the problem in a Cal 1 class, this part of the problem is the non-calculus part. It's getting it all set up and creating your function. Then we go do something. But let's talk about that function because we graphed secant and cosecant last class, didn't we? Could we graph that? If I asked you to graph that function, h of theta, right now, could you do it? Should I give you a quiz on doing it? Okay. So then I'm not going to give you a quiz, then you better lead me through it. How would you graph that if you were asked to graph that? What would you do? Graph the sine one instead first, right? So first thing I would do is I would graph, I'll just put y equals 2.5 sine theta. Why are you using sine theta? That's what you do for cosecant, right? If it was secant, you would do cosine, right? So I'm going to graph this. Also, I'm using theta. Do you want me to use x, or is theta still okay? It's all right? Okay, so what do you do now at this point? Okay, so how do you do that? Yeah.
You put x equal to 0, then x equals 2 pi.
Okay, so we're going to set the argument, which in this case will be theta, right? I'm going to set it equal to 0 and 2 pi, because that's the standard we do for sine. So 0, theta is 0, and theta is 2 pi. So please make sure you understand I'm using theta instead of x. All right, but that just gives me two really nice points, right? 0 and 2 pi. And this is a sine function, right? So since it's a sine function, where are my x-intercepts?
In the middle.
In the middle? At pi here, and at the two endpoints, right? And then you cut these into the quarter marks. I think we've done enough of this, hopefully. Pi over 2, 3 pi over 2. And then you would plug in a test point, wouldn't you, at this point? And I'm going to trust that you could do this, all right? You could test this. What you would get is 2.5 here, and it would go up and then down here, negative 2.5. And you would get this curve here. Now I'm drawing it dotted. Why am I drawing it dotted? Because this is the sine function, and I'm not trying to graph sine, I'm trying to graph cosecant, right? Notice I put my amplitude there, 2.5, okay. Now to draw the cosecant, what do I do at this point? Draw your asymptotes. Where do you draw those? Where do I draw them? Just anywhere I want? Wherever I have x-intercepts. So I'm going to have an x-intercept here. It's going to create a vertical asymptote. And then here. And then here. Like that, right? And now time to draw it. And the drawing of cosecant, there's really not a whole lot to do now. You just draw those little U-looking things. So I'm going to have a U that looks like this. And then I have a U that looks like this. Okay. Right, that would be it. Now, this is what we did last time. There's nothing new here in terms of what we've done, but I've connected it to a word problem now, haven't I? And I want to go back and draw the picture again. I'm going to do it real quick. I've got my ground, my radar, whatever. I've got my plane. Okay, and he's flying this way at 400 miles an hour, whatever. And then if I connect from here to here, this is a distance, it's h, and this is the angle theta, right? Okay? This picture gives you what that measurement of h is as a function of theta. So check out how, see, because before this was just a picture and it didn't really have meaning to it. But look at what this is saying. And I'm going to intentionally go with pi over 2 first. What would happen at pi over 2? So what would if your angle is pi over 2, where's the radar station pointing? Straight up, right? And what would the distance be? According to the graph, at pi over 2, how far away is the plane? 2.5, which makes sense because he's directly overhead. So the altitude is the actual distance, right? Now let's back it up a little bit. Let's come this way over here. Now my angle is smaller than pi over 2, right? So that means I'm over here somewhere. If I go up there, now do you see that I'm higher up? I'm further than 2.5? Yes? And what would happen if this angle gets smaller and smaller and smaller? That means the plane is further and further away, isn't it? Yeah. So as this angle gets smaller, right, the distance between me and the plane gets bigger. Why can't we have an angle of 0? Because if the angle is 0, you're looking straight on the ground, but the plane is 2.5 miles high. It's impossible for me to actually have an angle of 0. I have to have some little angle. And that means the plane would have to be really, really far away. Does that make sense? So if you approach 0, if your angle approaches 0, the distance between you and the plane is becoming infinitely large. That's pretty cool, right? I mean, that function is perfect for this situation. And then what happens if we go past pi over 2? So now our angle is like, here's pi over 2. If we go past it, like this, now the distance is bigger than 2.5. And what would be all the way around? There's 0, right? All the way around would be pi, wouldn't it? But again, I can't get to pi because the plane is off the ground. So if I've got a little tiny, tiny, tiny angle here, that means that plane is really, really, really far away. Make sense? Okay. So in the calculus class, we're actually only concerned with that part of the graph right there. That part of the graph right there is the part that gives us all the information we need for the problem. Okay? So hopefully that shows you that there is some usefulness of this. Now, I had the radar station tracking it, but really, it's probably more like a gun wanting to shoot the plane down, right?
Yeah, the plane will never even fly over the radar.
Yeah. It's amazing if you look back in history, well, I've had several students email me asking me where I took art classes. I'm kidding. So that's a castle. So if you go back and you look at, the history of mankind, humankind, humankind. Don't want to upset anybody. Right? If you look at the history of humankind, our need to kill one another has been a huge motivating factor in technology, hasn't it? Yes. In advancing. So you think about the simple idea of storming a castle. And, you want to lob fireballs and all sorts of things into the castle, right? Well, you could just randomly throw something into the castle. But we soon figured out that, you know, the path here is a parabola, and that all things travel through parabolic paths. Okay, well, once we figured that out, we studied, you know, quadratics more, and we could actually predict where things would land. So instead of just like randomly throwing stuff, we could actually pinpoint it. And now we're to the point where we can pretty much drop anything wherever we want, you know, within a few feet from anywhere in the world. But that's a different technology. We're not lobbing it. But the idea is the same. The mathematics behind this simple parabola allowed us to become better at doing this, right? So, and then you think about, you know, World War II, nuclear weapons, right? Those were pushed because it was a race to see who would get to it first, right? And we put a lot of time and energy into that. So, you know, motivating factor there, right? The fact that we don't get along in general, we just don't get along. All right, enough of that. Let's talk about phase shift, 7.8. Okay, so I'm going to ask you to remember something from college algebra. And why not talk about a parabola? All right, so we all know what this looks like, right? X squared. That's just your basic parabolic, right? That's your basic function, yeah? It goes through the origin, 0, 0. So when we learn that in college algebra, we then start to learn how to shift things around, how to move things and reflect things and all that. So if I change it, I'm going to still call it f, but I'm going to change it. If I do x squared plus 2, what effect did that have on that graph? It moved it up 2, right? This would just move it up by 2 units. So take that picture, move it up by 2. But there was a big difference between that and this. Where I placed that plus 2 had a huge impact on what actually happened with the graph. If I did the functions like x squared and then added 2 on the outside, then it would move it up or down. If that was a negative 2, it would move it down. But if I put the plus 2 inside with the x before it gets squared, then that has the effect of moving it either left or right. Which way does it move in this case? It moves left 2. Now, do you remember in college algebra being told that the left-right shifts are always like opposite of what you see here? So like if you see a plus 2, it moves it to left 2. You see a minus 2, it moves it to the right 2, right? This shift is what you would think. Up, you know, positive 2 is up 2 and negative 2 is down 2. So these are always like kind of counterintuitive against what you would think. This all ring a bell? Yes? Okay. We're going to be doing the exact same thing now with our trig functions. We are going to try and move them left and right. Up to this point, here's what we've been able to do. If I start with the standard sine curve like that, I can change its period by changing the number in front of x. So if I wanted to make this thing do more cycles more often, then what I can do is change it to like sine of 2x. And that would have the effect of doing these waves. You would do more waves in less space. Right? So if I change that to a 3, it would compress it even more and you'd get more waves. And that we could figure out where these starting and ending points were from just setting 2x equal to 0 and 2 pi. That's how we determined where it started and stopped, right? Okay. I could also move this thing up and down, couldn't I? Right? And to do that, what would I do? Just add a number on the outside, add or subtract, they would move the whole thing up or down. What we're going to do today is we're going to take any of these pictures and instead of changing like this spring, instead of stretching or compressing the spring, we're just going to take it and just move it left or move it right. And that's it. That's a phase shift. All right? Just changes where it starts and stops. So it's going to be very much tied to this idea. All right? Good? Okay, so let's start to come up with the general formula. And we're going to start with sine, then we'll do cosine. So for sine x, We have I want to copy the book's way of the notation so that when you do your homework, everything will match up. Okay, so the book uses A sine omega x. That should look familiar. We've talked about A being the amplitude, omega. We use omega to get the period. But then we have next to this minus that, and then plus B. I don't like the letters they use here, but they do. Okay, so this is, you can do this, or you can draw the line all the way through. Anyone know what letter that is? It's a Greek letter. No? It's phi. Phi? Some people say it phi. And there's a big online debate about whether or not you say it phi or phi. I don't care. I'll say it both. I use both equally, try and be fair. But look, at the end of the day, this is a number, right? This is a number, this is a number, and this is a number. The only thing that's a variable in the problem is the x. So this is like the general look of a sine function. Everything we've been doing up to this point has not included this piece. I may have put like 2.5 here, maybe I put like 4 here, and then I said like plus 2 to move it up 2, right? Now we're including this new piece. So how does this change things? All right? So first thing, amplitude. What is our amplitude? Well, the amplitude is still the absolute value of A. Nothing changes there. If I want to know the amplitude, I just have to look at that number, take its absolute value. All right, what about period? Well, good news. It's still 2 pi over omega. Wasn't that the formula I gave you before? Do you remember me giving you that formula? That all you have to do is take 2 pi and divide it by omega, and that will tell you the period. That's that's the distance between waves. So you have a full cycle, and then that's a period, and then the next period would be the same distance. What about the phase shift? All right, this is new, okay? So this is the new thing for today. I'll put a little star next to it. This is new stuff. The phase shift is going to tell you the left or right shift. And this will be always equal to phi over omega. Now there's something tricky in here that always gets students. And that is the fact that the way the formula is written here, it's minus phi, right? Minus phi. So when we say here phi over omega, it is that number ignoring the minus. Let me give you an example. Let me give you a specific example. As an example, if we did y equals negative 3 sine of 4x minus pi over 2 plus 3, that looks like that up there, right? All right, let's first identify what's A, what's omega, what's phi, and what's B. Let's just identify each of these, make sure we're all on the same page here. So what is A for us? Negative 3. So I'm not asking for amplitude period, I'm just saying the letter A in the formula is negative 3, right? What is omega? 4. And then what is phi? So this is the part that I think is the tricky part, okay, that people get hung up on. Phi is this number. If that's a negative, it's just that number. So it's just pi over 2. All right, that's what phi is. And then what's B? 3, right? Okay. So with that information, what's the amplitude of this thing? Well, it's the absolute value of negative 3, which is 3. What's the period? 2 pi over 4, which is pi over 2. Reduce the fraction. And then what is the phase shift? I'm just going to put PS for phase shift from now on. What is the phase shift? So you're going to take omega, which is pi over 2, right? I mean, sorry, phi, which is pi over 2, and divide it by omega, which is 4. So I'm taking pi over 2 and dividing it by 4, which is the same as pi over 2 over 4 over 1, which is the same as pi over 2 times 1 over 4, which is pi over 8. So just rewriting that as fraction over fraction, flipping, reciprocal multiply, get pi over 8. All right? Now, the fact that this is our phase shift, right, means that we took our graph and we moved it to the right by pi over 8. So the whole picture got moved by pi over 8 to the right. This all clear? Now, where it kind of gets tricky is if I change this problem, and let me write it down because I'm not going to take a shortcut here. Let me just give you a new one. What if I give you y is equal to 5 sine of 2 pi x plus 3 minus 1? Let's go through the same things. Let's identify A, omega, phi, and B. So A, omega, phi, and B. I'll tell you why I don't like phi, all right? What's that? Looks a little like theta, yeah. But it looks more to me like what's called the empty set. That's the set that has nothing in it. So any military people might recognize that as being how you write 0. Because in the military you don't want to confuse that with O, the letter O. What's that?
Are you Air Force?
No. Am I what?
Air Force?
Air Force?
I was just wondering if you were in the Air Force.
This is my drawing, right? I mean, you can tell I've been around planes. No. No, I'm not. My dad was Air Force, though. Okay, so in the military, we use this for 0. But in mathematics, it's not 0, it's the empty set. Now, what is an empty set? All right, so look, if I give you, that's supposed to be a set of braces. If I give you this set of numbers, that is the set, it's like a basket that has in it the numbers 1, 2, and 3, okay? This set has numbers 1, 2, and 3 in it. This set has what number in it? 0. And this set has what in it? Nothing, okay? This set right here is the empty set. It's the set of nothing. This right here is the set that has the number 0 in it. 0 is something, right? So 0 and this are not the same thing unless you're in the military. So it gets very confusing. And then you have phi, or phi, that it's technically not, I mean, if you draw phi properly, it doesn't look like the empty set, but when, every day we're doing it here on the board, it looks kind of like an empty set. That's why I don't like it. But that's what the book's using, so we're going to stick with it, all right? That was off on a tangent, sorry. All right, what's A, omega, phi, and B? A is 5 omega, 2 pi, and phi. Negative 3. This is the one that gets people. Because the formula says it has to be a minus, right? There's not a minus. The only way to write that as a minus is if you change the plus to a minus negative 3. Do you see? That's the same as plus. And now it looks like omega x minus phi, and that means phi is negative 3. So you could say it's the opposite of what you see. Like if you see a negative pi over 2, then it's going to be pi over 2. If you see a positive 3, it's going to be negative 3. If you like it that way, you can remember it that way. All right, negative 3 here, and then b is minus 1. All right, let's actually do an example. Let's graph something, all right? And I have good news. The good news is that nothing is going to change in the way we graph these. Nothing at all. In fact, let's just graph that one right there. Let's graph that. Okay? All right. So if we go back and we think about what we've learned over the last 2 or 3 days of class, first thing we want to do is understand we're graphing a sine function, and that all sine functions look like this, and have x-intercepts here, here, and here. And what we wanted to do was get that point and that point, right? And then draw the rest of it. So to get the beginning and ending, I set the argument equal to 0 and 2 pi. Now my argument's different, isn't it? Look at my argument. It now has this plus 3 in here, doesn't it? That's going to change things. It's going to make this computation a little bit ugly. I'm going to set 2 pi x. Oh, man, I started you off with a pretty tough one here. Should we do it? Yeah, let's do it. Okay, set that equal to 0. Not tough, but I mean, it could be nicer for the first example. 2 pi x, I forgot the plus 3, equals 0. Plus 3 equals 0. And then 2 pi x plus 3 equals 2 pi, right? That's what I do. Set the argument equals 0 and 2 pi. All right, let's solve this one. You can already see it's going to be, question?
You don't use the negative 3 only when you're using for phi?
That's right. Only if someone asks you to identify what phi is, you're going to do this. Now, what if I ask you what the phase shift is right now? Then you could use this, right? Because you're going to do phi over omega, right? Okay, but that's it though. If I'm asked on a test, I'm going to give you this, and I'm going to ask you to graph it. That's what I'm going to ask you to do. You should be able to do this, but it's not as important to me. All right, so when I solve this first one, I have to move the 3 over first. So I'm going to get 2 pi x equals negative 3, and then I have to divide both sides by 2 pi. And I get some weird number. This is crazy looking. Negative 3 over 2 pi. Now, that is a number, right? It's a number. Whatever it is, it is. And then I have this one over here. I have to solve this. So again, I subtract 3 from both sides. And then I divide through by 2 pi again. And that again is a weird looking number, isn't it? But it is a number. And what I need to do now is plot those, don't I, on a number line? So where are they? You have to be extremely careful at this point to make sure that you put them in the right order. Which one of those is to the left and which one's to the right? It's not always going to be that this one's left of this one. Not always. Okay? So is this a positive or a negative number?
Negative.
How do you know? Because negative on top and positive on the bottom, right? So that's a negative number. Is this negative or positive? Positive? Why? Why is that a positive number?
There's no negative in front of the entire term, right?
That wouldn't be enough.
It's just a minus 3.
Pi minus.
I know 2 pi is bigger than 3.
2 pi is like bigger than 3, right? It's like 6 point something. Because what's pi? Pi is about 3.1415 something, right? 2 times that, that's like 6 something. 6 minus 3 is a positive number, right? So that's positive over positive. That's still positive, yes? That's how you can tell this is a positive number and that this one is negative. So I know that that one has to be to the right of this one. Now, the negative 3 over 2 pi, I put that there. And then the other one, 2 pi minus 3 over 2 pi, I put that over here. Now, I also know that these are x-intercepts, aren't they? Because this is a sine function. Now I need the middle point. And do you see that middle point's not as nice as it's been? What is the point right in the middle of those? So how do we find that? We've done this many times. Yeah. Add them up and divide by 2, right? Add them up and divide by 2. Let's take our time through that. I'm going to add those two together and divide by 2 to try and find that point. So I'm going to take -3 over 2 pi. I'm going to add to it 2 pi minus 3 over 2 pi. And when I'm done adding those, I'm going to divide by 2. And when I get that answer, that will be this middle one, right? So when you add those two together, what do you get? Can you add these two fractions together right now? Yes, they have the same denominator, 2 pi and 2 pi. So all you do is put the numerators together. -3 plus 2 pi minus 3. So it's 2 pi minus 6 over 2 pi over 2 over 1. How about I say 2 over 1? That way I can flip it. And when I do that, I'm going to get 2 pi minus 6 over what? 4 pi. Does every single term in both the numerator and denominator have a factor of 2 in it? They do, right? So can I reduce everything by a factor of 2? Yes? And what would this become? Pi minus 3 over 2 pi. So all I did was just cancel the factor of 2 from everything. That's it. That's the middle point. See, on an exam, this is what I want to make sure you can do this sort of arithmetic. And it's really the more important part of this arithmetic that we're doing here is, again, for calculus. When you get to calculus, you've got to be able to find these points, these middle points. So, and it's good, fun practice, right? Do I have an x-intercept there? I do. All right, we now need to go get the next 2 points, which are going to be here and somewhere over here. I'm not sure where it lands. It might be negative, it might be positive. Just for now, I'm just going to put it there. I don't know. Okay? And find the middle of these 2 now. So add them together and divide by 2.
Couldn't you just do what you did with the first one, except multiply by a quarter instead of half?
Do what?
You know how you did the first one, where you add them both together, and then you divide it in half, or 1 over 2? Could you do it by a quarter? Finding the quarter mark, right? What we're looking for?
I'm just thinking to make sure that would work. So if I take that, I add them together, and then take a fourth of it. Yeah, it should work. It should work.
So we take the 2 endpoints still, and
What I've shown you is to get the middle number, you just start with these 2 endpoints again and then do the same routine. I think what you're suggesting is...
And then what I'm saying is, you found the first middle piece, and you divide it in half, right? And you're finding the quarter mark, just multiply by a quarter.
You're saying right here, replace this with a 4
Yeah.
instead. Yes?
Essentially, yes.
Okay. I think we'll get the same thing. I'm just making sure mentally that that would work. I'm pretty sure it would.
Because that's what I've been doing with the other ones.
Yeah.
Like, it works. I just
Okay.
don't know if there's like a flaw.
Yeah. No, because you're basically finding out, when you do half,
You find the middle.
you could do the quarter, and then you could actually do 3/4 here to
Right.
do that one also. Yeah. I guess the reason why I'm doing it this way is just every time I do this is just another practice of you finding the middle, right? If you find your own like short way that you like to do it, you can. I'm going to continue to do it this way because every time I do it, I feel like my arithmetic gets better. So I'm taking these two endpoints, adding them up, and dividing by 2. So what do I get when I put these together on top? Pi minus 6 again, over 2 pi, over 2 over 1. We agree? And then when we put those, flip it, we should get pi minus 6 over 4 pi. And this time I cannot reduce that, right? Any further?
That would have worked.
Yeah. Because we would have had 4, so that would have been 8 there, and then you would have reduced everything. Well, hold on. Can we revisit that in a second? Let's revisit that in a second, all right? The reason I'm hesitant to say yes is because I have some serious doubts. I think it works when you start at 0. Like if you start at 0 and go out, then this will work.
Yeah.
Like your method. But once we phase shift it, I think it falls apart.
Okay.
But let me finish this and then I'll show you. The best way in mathematics to ever show something is not true is to find one example where it doesn't work. Right? So if I can just show one example where it wouldn't work, then we would put that to bed, wouldn't we? All right, what is this here? I've lost my spot. Is it this one? Yep, okay. So this right here is pi minus 6 over 4 pi. Now to get this one right here, I'm going to add these two together and divide by 2. So we take pi minus 3 over 2 pi, add to that 2 pi minus 3 over 2 pi, and then divide the whole thing by 2. Since we have the same denominator, I'll have 2 pi here, and then what's my new numerator there? 3 pi minus 6. And then if we reciprocate, 3 pi minus 6. Are y'all okay with me doing that? You like that? Sound effects too if you want. And we cannot reduce that, right? We don't have a common factor in all of those. Like we don't have a common factor in 3, 6, and 4. So that's it right there. This right here is 3 pi minus 6 over 4 pi. Graph time. Try and fill it in. I need a test point, don't I? What point should I test? The first, what do you mean the first? Do I want to test this one? Now remember, that's the x-intercept. So you know you get 0 out there. We're not interested in that. We're interested in what's happening here. So we want to plug this in. We want to plug that in for x into the original function. So let's take a look at that function. I have long since erased it. What was it again? 5 sine plus 3. Okay, so I'm going to take this and I'm going to plug this in for minus what?
1.
Minus 1. Ooh, I forgot about that part. Okay, so this is going to get plugged in for x, right? So let's see what happens here. We get 5 sine, 2 pi times this, pi minus 6 over 4 pi, and then plus 3, and then I've said when we graph this with the vertical shift to ignore this, right? Ignore this until the end. At the end, we're going to just move the whole graph down 1, right? So let's plug in here. When you do this, these pi's cancel, don't they? Yes? And then this and this becomes a 2. With me? Okay, so here's what I've got. 5 sine, and then I've got pi minus 6 over 2 plus 3. And that looks pretty ugly still, right? But I have a 2 here and I have 2 terms. Can't I split that into 2 fractions? Can't I do pi over 2 and then minus 6 over 2? Yeah, that's legit. So splitting that up into 2 fractions, negative 6 over 2 is negative 3, plus 3. And these go away. And you just get sine of pi over 2. So what is sine of pi over 2? 90 degrees, y coordinate, 1, right? And so 5 times 1 gives us 5. So we would be here at this mark right here, we're up at 5. This is 5. And that, by default, forces the one down here. Maybe I'll exaggerate this a little more. Hold on. Let's make 5 way up here. And then this will be negative 5 down here. And so I know it goes like this. And then how do you feel about moving the whole thing down 1? Could you do that? Take every point and drop it 1? Just be careful. This point right here is not on the y-axis, right? It's not on the y-axis. Do y'all agree with that? This point is not on the y-axis. Why did I move it on this side? Kind of got lucky. It is a negative number, isn't it? Pi minus 6. Pi is about 3 something. Minus 6, that's a negative on top. And you divide it by 4 pi, it's going to be a small negative number. Okay, I'm going to let you move the whole thing down. I think I started with something a little bit too messy. Would you agree? I think that's a little messy. Let's do something that's a little more in line with something that you would see on a test. All right? All right, let's try this. How about y equals 1/2 secant of 3x minus pi. Oh, wait, you know what? Before we do this, can we visit that question you had? Let's visit that real fast. So if I can come up with an example that doesn't work, then we'll be done, right? So what if I take the point -1 and let me get something like 13?
Yeah.
So what you did was added these together, which would be what? -1 plus 13, and then divide by 4 instead, right? So this would be 12 over 4, which would be 3, and that's all you would do? You see, that's not going to work.
Right. I think it only works for the...
It only works if you start at 0.
Right.
It only works if you start at 0, because if you start at 0, then whatever this is, right? Check this out. This is why it works. I'm trying to give you more of an illustration. Start at 0, and let's just call this A, right? Then if I add these two together, I get A, and if I divide by 2, that's halfway, right? But if I instead divided it by 4, that would just give me 1/4 of A. And so yes, I would be 1/4 of the way there.
Right.
But it's only because when I added these two initially together, I had A. Does that make sense? But if this is different than 0, then you're not going to have that. So yeah, this doesn't work, unfortunately.
Damn.
Yeah. Now, what you could do, if you really wanted to do it, you could take the difference of the two, 13 minus -1, and divide by 4. And what that's doing is it's taking the distance between these two and dividing it by 4. So that would be 14 over 4. That's the distance 14 is the distance between them. Dividing by 4 cuts it into 4 pieces. And then what you would have to do is take that and add it to this.